All right. So yesterday we were able to start taking a look at derivatives as rates of change. So not just something that we're computing, but bringing it back to sort of the original purpose. Why do we need to have things called derivatives? And why does finding slopes of curves actually help? And so it turns out that we sort of have three different ways of describing motion, and maybe we should write these up at the top, that we have position. We usually notate that as S of t or X of t, all right? We can determine a particle's position, but if we take that first derivative, we can actually determine the velocity of the particle. So we could say S prime of t equals X prime of t, or that's our velocity function. And then if we take the derivative one more time, so the first derivative of velocity, but the second derivative of position, so second derivative of position or first derivative of velocity, we'll end up with acceleration, okay? Now, just to kind of get us thinking about things, right now we're saying if we have position, we can find all these other things. We can find velocity, we can find acceleration. If we had acceleration, any ideas on how we would find velocity?
Finding antiderivative.
Yeah, exactly. If we undo this derivative, we'll end up with velocity. And similarly, if we have velocity and we want to get back to position, we have to be able to undo that derivative, okay? And so we're going to spend a lot of time in sort of the second half of the class looking at how we undo derivatives. But for right now, let's focus on how we actually take derivatives, okay? All right, so we were able to describe some motion. We looked at a bunch of graphs. We were able to find information from the graph, but then also from the equation, okay? Each graph told us different things. And at the very end of class yesterday, we were working on this problem right here where we were really interpreting what the question meant. Find the acceleration when the velocity is 0, okay? And so one thing I really want us to be practicing is that idea of how do we take a word problem, velocity is 0, for example, and translate that into an equation so that we can connect that question to a specific process, okay? And so what we're gonna do right now is we're gonna take a look at a third example, all right? And we are actually going to, and this should look familiar if you've taken a look at quiz 5, there's this question very similar to this on quiz number 5, okay? So if you are sort of looking at the quizzes in advance, one thing I would recommend, so one recommendation is to look at the quizzes in advance so that you know what to focus on during lecture. Okay, some of us are already doing that. Some of us are not doing that yet, and that's fine. I think we all have different study techniques, but if you feel like it's really hard to go back and figure out where things are in the notes, it might be a good idea to start previewing content so that you can make that connection a little bit tighter for yourself, okay? But we have a graph here, and we're gonna be answering several questions about this. And we're also going to be focusing on this part, another way to ask the question. Okay, another way to ask the question. And I think that one of the things that makes this unit a little bit trickier is that there's a lot of different ways to ask you to find certain things. And so I want to make sure that we spend time in class making sure that connection is really tight. Okay. And so let's take a look at this graph, all right? Now, right off the bat, what can you tell me about this graph? Just describe some things. What do we see here?
Looks like a sine wave.
It does actually look like a sine wave. Good. Okay, so it's got some sort of, it goes up and then it goes back down and then it starts to go back up again. Okay. What else do we see? Time and position in seconds and meters. Yeah, let's go ahead and highlight that. So if I zoom in a little bit, it's still kind of blurry, but that's on my end, not on yours. We've got time on the x-axis and we have position on the y-axis. And so maybe we'll just make a note that this is in meters. I think that little m can be a little hard to read, and this time is in seconds. Okay, good. And so this function goes up and down, but we might even say that this is a s of t or x of t graph. Okay, so every y value here, which looks like it's between -4 and 4, exactly. So in this case, it looks like the highest point is at 4, the lowest point is at -4, and those values would represent position, okay? And so we could maybe say that y values represent position, okay? What else do we notice before we even look at the questions? Are there any other things that we've kind of looked at on graph that maybe seem like they pop out for you? Possibly an odd function. Now that's a great observation. I know we talked about even and odd functions yesterday. Unfortunately, we can't tell that it's an odd function because we don't know what's happening on the other side. Okay, so if we had a more full picture and we knew that it went down like this, then I think you would be right. It would be an odd function. But it's entirely possible that maybe the other side looks something like this. Okay, yeah. But I love that connection to yesterday. Oh, we have initial position. Okay, so yesterday we talked about initial position. Where might that be? Yeah, so right here, we have an initial position. So maybe we could say that S of 0 equals 0. In other words, initial position. All right, where time is 0, good, good. And it looks like I missed one here. There are 2 humps where it looks like velocity might be 0. Oh, okay. And so if we kind of trace this curve, we might say that the slope on this side is positive, and on this side it becomes negative, which means at some point right in the middle, we have a horizontal tangent line, okay? And it looks like that might occur again down here, where we have a horizontal tangent line, right? And I really like the language that Luca used here, that horizontal tangent on a position graph is the same as saying, where is V of t is 0, okay? So horizontal tangents, those pink lines that we've sort of sketched out here, horizontal tangents on the position graph are where the velocity is going to be 0, okay? Now, let's look at one more thing before we go to the questions here. This region right here, would you say that the velocity is positive, negative, or 0? Yeah, this first part, all those tangent lines, if we were to draw them, are all having a positive slope. Whereas this next region, what about the slope here? Negative, negative. Okay, what about this region here? Still negative, good. And what about this tiny little region here before we cut off the time? Positive, good, good, good. Okay. All right, so let's take a look at these questions, okay? Sometimes I think it's useful to do a little bit of a brain dump. This might be a really good study technique to help you figure out like what kinds of questions typically get asked. A lot of times what you notice about a graph are actually what the questions are going to ask you to notice about that graph, okay? So let's take a look at question A. Question A says, what do the Y values of this graph represent? And explain how you know. So I think we've already answered this question. We said that the Y values represent the position, okay? And the units would be in meters, but I think more accurately, we would say they represent the position of the function, okay? So let's write that in. The Y values of this graph represent position of the particle. And how might we say we know that? Like, how did we know that based on the graph that we saw? Yeah, the y-axis is labeled that way, right? It says position right up here. So we can say the y values of this graph represent position of the particle since the axis is labeled position. Okay, so that one doesn't need to be a really in-depth explanation. I like to ask that question because I think all of our answers after are going to depend on what that graph is telling us. So if we have a position graph, we have to read it like a position graph. But if we had a velocity graph, we would have to read it differently. Okay, it would give us different information. And so as simple as this question sounds, it's so important to read those axes and make sure you know what it's actually showing you, okay? All right, second question and maybe third question kind of go hand in hand. Where are the Y values positive and where are the Y values negative? All right, so let's start with B. Where are the Y values positive here on the graph? Okay, so I see sort of competing answers here. Remember, we're looking for where the Y values are positive. All right, so I'm not asking about slope. I'm being really specific and I'm saying Y values. All right, and so if we're looking for positive Y values, that's going to be all of this region right here. That's all going to have positive Y values. Okay. that means that all of our negative values are from 6 to the end of our graph, all right? Now, one thing I want to be really careful about is whether we're using brackets or whether we're using parentheses, okay? So when we say where are the y values positive, this y value at 0 is actually 0. And 0 is not positive and it's not negative, okay? The y value at 6 is also 0. That's not positive or negative, it's just 0. And so we want to describe our interval using parentheses, like Matt says, because we don't want to include those points. It's like really close to 0 and all the way to really close to 6, okay? And so a note we might make to ourselves is parentheses, because we are not including x equals 0 or x equals 6, okay? So let me just pause for a moment. And let's see what questions come up. So I see one right here. What if one point is on 0, but the other isn't? Okay, so if it does include it, then we use a bracket, okay? So for example, if I wrote 0 to 6, this is not including 0 and 6. If I want to include 6, but not 0, I would say 0, 6, bracket. If I want to include 0, but not 6, I'll do include 0, but not 6. And if I want to include both of them, bracket 0, 6, bracket. Okay, so the bracket means we're including it, but the parentheses means we're not. I feel like the bracket parentheses is sort of the new true false, where sometimes students are like, you don't make it very clear. You're like, it could be either one. So just make sure you make it really clear for me whether you're doing a bracket or a parentheses, okay? All right, so that's where the y values are positive and the y values are negative, not including 6, all the way to 10. Now, do we include 10 or not? Or should we include 10 or not? All right, I see a no. I see a yes. Ooh. All right, let's see. So if we zoom in a little closer here, the y value at 10, that looks like it's negative, right? Like negative 3.5 or something. It actually doesn't matter if there's an arrow because I'm saying this is 9, this is 10. This value is still negative, right? So I do want to include 10, but I don't want to include 6. So I'm going to say parentheses 6, 10, bracket. Okay. So we'll say parentheses 6 and then 10 with a bracket. Okay. Now, one way that I could ask this is, where are the y values positive, where are they negative? But in a more conceptual way, all right? What we might see in practice problems that we find online is someone might ask us this. Instead of saying, where are the y values positive? They might say, when is the particle to the right of the center point. Okay, so someone might say, when is the particle to the right of the center point? And in your brain, you would say, they're asking me to find where are all the y values positive. And then you'd go to your graph and find out where those y values are positive. Okay. How would I modify that sentence for part C? Where are the y values negative? What is a more conceptual way that I might ask you that? Exactly. When is the particle to the left of the center point? Okay. So typically, when we say positive, we're saying to the right. It is sort of a right-hand dominant society, I suppose. And then when we say things that are negative, we're thinking to the left, much like an x-axis, that if we go to the right, we'll have positive, but if we go to the left, we'll have negative. Okay. So I'm going to cheat a little bit. I'm going to copy and paste this. Oop. And we're going to shrink this to make it fit. So another way of saying where the y value is negative is to say, when is the particle to the left, not the right, but to the left of the center point? Okay, so this is a really good question. Let us answer part D, and then let's kind of imagine what's happening aside from like this sort of sine graph thing that we're seeing, okay? So last question for this sort of group of questions. Where are the y values equal to 0? So according to our graph, the y values are equal to 0 when time is 0 and time is 6. Okay. Now, knowing what we said about left and right, what might be another way of saying, where are the y values equal to 0? Good, good, good. So we might say, when is the particle at the center point? Okay, when is it at the center point? So why are we saying all of this, right? I think, Abby, you bring up a really good point. Like, I'm telling you this, but like, how do we know? Okay. And so let's go back up to the graph for a moment. All right, I'm going to erase the interval notations over here. All right. But when we're looking at a graph like this, what we're really thinking about is, how is a particle moving? Okay. And so what that kind of looks like is, if we have, this is much more effective when we're in the classroom and I get to walk back and forth in front of the class, but we'll kind of do a little diagram here. So I'm just going to give this a center point. Okay. And now, because we're just kind of learning this stuff, we're imagining that this particle or whatever this object is only moving left or right. So it's got a very fixed direction in which it's moving. It's not going up or down. It's not going diagonal. It's literally only moving left or right. Okay. And so we establish a center point because it makes it easier to describe the motion relative to that center point, okay? So at the beginning, when we start measuring, that particle is like right here, right at the center, okay? And then it goes to the right. What happens at this moment in time at 3 seconds? What is that particle moving? Is it not moving? What's happening? Okay, yeah, it's at rest. Now, how do we know that? Because we get to sort of the top of this bump and that slope or velocity is 0, okay? So imagine that you are sort of going to the right, going to the right, going to the right. You stop. Now you're coming back towards the center point, okay? So you are moving to the right, moving to the right, moving to the right. You stop and you turn around and come back towards the center, right? Has everyone in here taken PE or gym class, like in high school? Yeah, okay. I think it's sort of a requirement in a lot of places. So you may or may not have had that experience, but you ever have, I forget what they're called, it's like the shuttle run or something like that, or some people call them suicides, where like you all start on a line and then you like run to the cone and you touch the cone and you turn around and come back. Yeah, pretty much. That's, if you ever played any team sports, you probably had to do that like a bunch for conditioning. Okay. So you sort of all start on a line, you like run to a cone, you touch the cone, you turn around and come back. That's exactly what's happening in this first bump. So you're running, you're running, you're running to this cone or the line. And in order to turn around, there's one moment in time where you are stopped, you turn, and you come back towards the starting line, okay? So in other words, if I were to draw this on this sideways picture here, you are running towards this cone, you stop, you turn around. And so this would be at t equals 3 is the moment that you turn around, okay? What time do you get back to the center point? Good, good, good. So at t equals 6, you get back to that cone or your starting line. Okay. So imagine you're in a gym, you run, you touch the cone, you turn around, you come back, and that takes you 6 seconds. Okay. And then maybe you have a PE teacher who really wants you to be in shape, and they're like, now you're going to run in the other direction to the other cone that I set up. And now you run away from the starting line, but in the opposite direction. And then you turn around and you start to come back. Okay, so the second half of things, let's maybe say that's in blue. After t equals 6, you go and you end up somewhere over here. You don't actually get back to the center point. Maybe that was too much fitness for you and you, you know, felt a little nauseous or something. And so you're like, I'm going to stop. What time did you stop at, according to this graph? Yeah, t equals 9 is when you stop and turn around. And then maybe your PE teacher was like, oh, we're only doing this for 10 seconds, so just stop where you are. So at the very end, when we stop measuring your motion, your position, that's at t equals 10. Okay. So you start at the beginning, you're fresh as a daisy, you run to that first cone, you touch it, you turn around, you come back. And then your gym teacher's like, oh, you got to go in the other direction now. And you're like, oh, and then you go all the way to the left, you touch that other cone and you start to come around towards your center point again. And then your gym teacher's like, oh, that's it. That's all the time we have for today. Okay. So hopefully these two diagrams side by side give us a better idea of what's happening here. Okay. But we can see that everything that is in the pink, well, that corresponds to these positive Y values. And everything in the blue, that corresponds to these negative Y values. All right, so the positive Y values tell you when you're to the right of your center point, whereas the negative Y values tell you about when you are to the left of your center point. Okay. So I see one that makes more sense, but let me get those 4 questions up here. How are we feeling about position and positive and negative Y values? Okay, that is a great question. So I will say this, the center point is not always the same as the initial position, okay? So maybe if we had a different graph, and if it started not at 0, but started at 2, okay? You can imagine that as your center point is still 0, but you started to the right of that center point. Right? Maybe you have that classmate in your PE class who's a little bit of a cheater and tries to get a head start on everyone by starting ahead of the starting line, and that would be that person. So they're starting to the right of the center point because it has a positive Y value. Yes, yes, yes. So this 0 is going to be your center point. Okay. Sometimes it's also your starting point, but not always. Cool. All right. So let's sort of shift gears a little bit and let's talk about slope now. Okay, because we are in the derivative section, we are in calculus, and so let's talk about the slope. We've already started to hint at there's 2 moments in time where that velocity is 0. Okay, so let's come back to our questions and see what they ask us about. All right, so what is, in part E, what is the slope of the secant line over the interval 1 to 7? Okay, so we're looking at the interval 1 to 7, and because I have brackets here, I am including 1 and I am including 7. So let's go back to our graph. Let's maybe do this in green, all right? And we'll draw that secant line from 1 to 7. All right, let's zoom in a little bit here. At 1, the Y value looks to be about 2. And at 7, what is our Y value there?
-2.
Exactly, it's going to be at -2. Right? So those 2 points, if I sketch a line between them, will give me the secant line that I'm looking for. All right. So let's grab those numbers. Let's go back down to part E, and then Evelina will come back and answer your question in just a little bit, okay? So let's go ahead and find the slope of that secant line. We've got a point 1, 2 and 7, -2. So to find the slope between these two points, I want to plug things into the slope formula. Y values go on the top, X values go on the bottom. We're going to be really careful about our signs here. So the first point I have is 7, comma, -2. And then the initial, or the first point in that interval was 1, comma, 2. Okay. We'll be careful about our mental math here. -2 minus 2 gives me -4. 7 minus 1 gives me 6. And this is reducible, so we'll get -2/3. And what units might we put on this? I think the units might help us with the another way to ask. All right, so on the top, our Y values are in meters, and on the bottom, our X values are in seconds. So -2/3 is really -2/3 meters per second, okay? And so if that is a challenge for you to find the units, I think that go back to what you plugged in, okay? So what did you plug in for the numerator? Those units will still be your top units. And then what did you plug in for the denominator? Those units will still be the bottom units, okay? Now, what is another way that I could say, find that slope? Right, and particularly in the context of motion, okay? So I could say average rate of change, right? And I love that first word average, but let's take what Juan has in here. Remember, the slope of position is velocity. So if I have average rate of change, I'm actually looking for average velocity, okay? So we can go down here and say that this is what is the average velocity of the particle from t equals 1 to t equals 7. Okay. So let me pause here for a moment and make sure that that connection between average rate of change and velocity makes sense for us. Okay, average rate of change isn't mathematically wrong, but if we're talking about position, my bet is there's going to be questions about velocity and acceleration, okay? So what is the rate of change? The rate of change in this context is velocity. So it's a little bit more accurate to say average velocity rather than average rate of change, okay? All right, Evelina, let's see, in part A, what was your question about part A?
There's a axis. The axis. Where is the axis? Is level position. You mean the Y axis or? Oh,
this just says axis. It doesn't have an.
So when I write A axis, it's. I see what you mean. I see.
Yeah, we're looking for. It would be more accurate. Let's put this in here that we're looking for the Y axis. Okay.
Okay, thank you.
Thank you. All right, we've got one last question here, and I think this is one that you actually already know the answer to, okay? What is the slope of the tangent line at x equals 0? And so if we go back to our graph and we look at 3, right, at 3, what is the slope there? That slope is 0, okay? So that is a great observation. When you're looking at a position graph, it's probably a good idea to identify where those horizontal tangents are going to be, because I bet that you'll get asked about those. Okay. So sorry for all the scrolling up and down today. It's hard to fit all the word problems on one page. But what is the slope of the tangent line at x equals 3? We could say that the slope equals 0. All right. And another way to ask this is exactly what folks said in the beginning, which is when is the particle at rest, right? When is it not moving? Another way to ask this question might be, what is the particle's velocity at 3 seconds? All right, what is the particle's velocity at 3 seconds? Since it's a position graph, you can just say the velocity is going to be the slope there. Happens to be the top of a bump, so we know that slope is 0. Okay. Let me squeeze this all on one page here. And before we move on to this last example, are there any lingering questions at this moment? All right, well, when you're working on quiz 5, a lot of these, another way to ask, all right? We've done some explanations here or some ways of writing it, so that should help you with the wording of some of those quiz 5 questions, okay? All right, let's take a look at the last question in 3.4. Not a lot to scroll up and down here, but we have a particle moving along the x-axis. So we're looking about that horizontal movement, like that shuttle run business, right? You run, you touch your cone, you turn around, you come back, that kind of movement. So a particle moves along the x-axis so that at time t is greater than or equal to 0, its position is given by x of t equals 2t cubed minus 21t squared plus 72t minus 53. At what time is the particle at rest? Okay, so before we start computing anything, let's take a moment and think about what kind of steps we might need. Okay, you folks did a great job yesterday thinking about what are these words trying to tell us to do in terms of procedure. So let's take a moment here. At what time is the particle at rest? What do we know about when a particle is at rest? Nice, nice. So let's jot this down. Let's see what other phrases folks come up with. So particle at rest is look for horizontal tangent. I'm going to add one phrase to this. Okay, look for horizontal tangent on position graph. Okay, on the position graph. Good. And we can even translate this further, that horizontal tangents means when is the slope equal to 0 on a position graph. Okay. Now, what is one more thing that I can say? Oh, instead of slope equals 0, how do we think about slope in the context of calculus?
If you set the first derivative to 0.
Good, good, good. So we have the slope is 0. So we want to say x prime of t equals 0. Okay, so let's sort of zoom back out for a moment and focus on this concept, right? So when we're saying at what time is the particle at rest, this is a really good thought process to go through. Particle at rest means we're going to look for horizontal tangents on the position graph. That means that the slope is 0 on the position graph. And algebraically, that's the same as saying, find that first derivative, set it equal to 0. Okay. And so if we were to translate this into sort of steps for us to think about, our first step might be find x prime of t. Okay, so take a moment now that we have our x of t function on the screen, go ahead and find your x prime of t, and then we'll jot that down. And when you get that, you can go ahead and type that into the chat. Let's see if we are in agreement. All right, I see 2 matching answers, a third in agreement. Good. And that minus 53 at the end, that goes to 0 when we take the derivative, right? So we'll end up with 6t squared minus 42t plus 72. Exactly. And we can have a minus 0 at the end if that makes us feel better, but it does when we have just a constant, that derivative goes to 0. All right, so after we find our x prime of t, what would we do next? We're going to set it equal to 0 and we're going to solve for t. Exactly. So we're going to set x prime of t equal to 0 and solve for t. All right. So let's take that derivative and we're going to say 6t squared minus 42t plus 72 equals 0. Now, before we start to panic, okay, that, wow, these are kind of really large numbers. And she said that she wants us to factor, and it's really hard to factor with big numbers. The one thing I would always look for first is their greatest common factor. That is the easiest way to make the numbers smaller and therefore easier to work with, okay? Now, it turns out that 6 goes into every single coefficient here. And so I can actually factor out a 6 and get t squared minus 7t plus 12. Okay. Now, I can make it even easier for myself by saying, let's divide that 6 away, because on the other side, 0 divided by 6 is going to give me 0. So I'll end up with t squared minus 7t plus 12 equals 0. And this expression, I'll give you a moment to factor that, I think is a lot easier to factor than the first thing we looked at, right? So that's a handy algebraic trick to know, is if you're working with bigger numbers, let's see if there's a way to make them smaller, okay? Anybody get a factorization for this quadratic polynomial?
Yes, 6 times t minus 3 times t minus 4.
All right, excellent. And then we're going to set each piece equal to 0 and we'll get t equals 3 and t equals 4. Okay. that means that this particle's moving along at t=3, it stops, goes in the other direction, and then 1 second later, it stops again. Okay, so t=3, t=4. We know that that's when the particle is at rest because we were looking for horizontal tangents on the position graph, which meant slope equals 0 on the position graph. And for us, algebraically, it means where is x prime of t equal to 0, okay? So that is the end of 3.4, and that should cover everything that is on quiz 5, okay? So I'm gonna stop the recording right here.